Namaste. Welcome to the next video of Machine Learning Techniques course. In this video, we'll implement logistic regression from scratch. Logistic regression is the workhorse of machine learning. Before deep learning era, logistic regression was the default choice for solving real-life classification problems with hundreds of thousands of features. It works in binary, multi-class, and multi-label classification setups. In this collab, we'll implement binary logistic regression from scratch and employ it for solving a couple of classification problems. In one of the settings, we have linearly separable classes and the other one has nonlinear decision boundary between the classes. The first problem can be addressed with basic logistic regression classifier, while the second problem requires an additional step of polynomial transformation before using logistic regression. These cases will provide an idea about how to use logistic regression to solve classification problems in those two settings. We'll set up more such cases for practice in programming exercise. Let us begin by importing basic Python libraries that are required for the implementation. We import NumPy for implementing components of logistic regression in vectorized form. Matplotlib and Seaborn is imported for visualization. The math and LaTeX libraries are imported for proper rendering of mathematical expressions in Colab. As a good practice, set the random seed. Random seed enables us to reproduce same results across different runs of the Colab. We have set the random seed to 1, 2, 3, 4. You can set it to any other number of your choice. In the first part of this exercise, we'll implement individual components of binary logistic regression one by one. The first component is model. As you know, the logistic regression classifier calculates the probability of a sample represented with feature vector x and belonging to class 1. So it finds out probability that the sample belongs to class 1 given its feature vector. It has two steps: linear combination of the features and sigmoid activation. Let us apply these steps on a single example to calculate its probability of belonging to class 1. The first step performs linear combination of features and obtains z. So z is calculated as W transpose x, where W is the weight vector and x is the feature vector. And z is a scalar, which is the linear combination of features. The second step applies sigmoid or logistic activation on z to obtain the probability. So we perform sigmoid of z and we get probability of the sample belonging to class 1 given its feature vector. The sigmoid function is calculated as 1 by 1 plus e raised to minus z. As we have discussed several times in the past, performing this computation example by example is not efficient. We can make it more efficient by rewriting it in vectorized form. The vectorized form enables us to compute probabilities for several examples all at once. We first vectorize the linear combination of the features, leading to its efficient computation. So the linear combination is obtained by performing a matrix multiplication between the feature matrix and the weight vector, and we obtain the resulting linear combination. Here, X is a feature matrix with shape n, m, where n is the number of examples and m is the number of features. The weight vector W has m components, and resulting linear combination Z is a vector with n components. So we get one value of linear combination for every sample or every example in the feature matrix. Let us implement linear combination in vectorized form. So we have implemented a function linear underscore combination that takes feature matrix and weight vectors as an argument, and it returns the linear combination of features for all the examples. in the feature matrix. And a linear combination is simply implemented as a matrix multiplication between the feature matrix and the weight vector. In the second step, we also vectorize sigmoid or logistic activation to obtain a vector of probabilities or activation. So here the input is a linear combination vector and output is an activation vector or the probability vector. The sigmoid function is applied on each and every component of this Z. So you can implement the sigmoid function by passing the result of the linear combination, and it returns the vector of activations or the probabilities. And we have implemented sigmoid as 1 by 1 plus exponential of minus z. So we use np.exp in order to implement the e raised to minus z. Further, we apply vectorized prediction or inference function on activations to obtain class labels. Specifically, if activation or probability is greater than threshold, then we label the sample with class 1, otherwise we label the sample with class 0. So we define a predict function that takes feature matrix, weight vector and threshold as an argument, and it returns the probability it returns the vector of class labels. So we implement predict as follows. So we first perform linear combination between the feature vector and the weight vector. So that's the linear combination. We pass the linear combination to sigmoid function that gets us sigmoid activation, and on that activation vector we apply np.where, and we check wherever the activation is greater than threshold, we assign the class 1, otherwise we assign the class 0. So again, this is a vectorized operation. So we have vectorized linear combination, sigmoid and the prediction function. And vectorization enables us to get prediction for multiple examples all at once. Now we will demonstrate the prediction with a couple of samples. Here we have two samples, each with two features, and we have added a dummy feature that is set to 1 and it corresponds to bias. So the original features were 20 and 2 and 2 and 2 for the second example. First example it is 20 and 2, those are the two features. And the weight vector is -1, 0 and 1. So since there are 3 features including the dummy feature, the weight vector will also have 3 entries. Then we simply call predict by passing the feature matrix and the weight vector and the threshold. So here we have set the threshold to 0.5. We can change this threshold to any other value depending on the problem that we are solving. Here we obtain the labels for both the samples, and both the labels are 1. So both the samples belong to class 1. Next, we'll implement binary cross entropy loss with regularization. The base loss without regularization can be obtained by setting the regularization rate to 0. The generic form of loss is as follows. So binary cross entropy loss, or BCE, is equal to BCE on training examples plus lambda times regularization penalty. So lambda is a regularization rate that controls the amount of regularization penalty to be used in the loss calculation. By setting this lambda to 0, we basically get only the binary cross entropy loss on the training examples. So we set lambda to 0, hence the second terms become 0 and we end up with the base loss. We use L2 and L1 regularization in logistic regression. With L2 regularization, the loss function is calculated as J of W. So loss function is the function of the weight vector. It is obtained as minus or minus 1 into sum over all n-training examples. We first calculate the product of the actual label into log of sigmoid activation for that example plus 1 minus actual label into log of 1 minus sigmoid activation for that example. So remember, sigmoid returns value between 0 to 1. Plus we add a regularization penalty scaled by the regularization rate. So lambda is the regularization rate, and since we are using L2 regularization, we add the L2 or the second norm of the weight vector. Similarly with L1, regularization, the loss function is calculated exactly as L2, but instead of the second norm, here we add the first norm as the penalty, first norm of the weight vector to be precise. In order to write the loss in vectorized form, we first calculate the term inside summation in vectorized form. So we represent this particular term inside summation in vectorized form. So we already know how to calculate sigmoid in vectorized form. So we basically write sigmoid in vectorized form. We take the label vector here, then we take log of sigmoid in vectorized form, which is the matrix multiplication between the feature matrix and the weight vector, and that's how we can calculate this term inside the summation in vectorized form. We call it as vector E. So if we substitute E over here, the base loss becomes J of W equal to minus 1 into the vector E, and this is, by the way, vector of ones, and after applying transpose operation on it, it has shape of 1 comma n, and E has shape of n comma 1. So what happens is that this has effect of, so when we do the vector multiplication, we get basically the summation of all the components in this error vector. So if we add L2 penalty, then L2 penalty can be calculated in vectorized form as W transpose W. So that is the second norm of the weight vector. And in case of L1, we basically sum up the absolute values of individual weights. So here we use the same trick and multiply it by a vector of 1, and this will basically give us the sum of absolute values of the weight vector multiplied by the regularization rate. So here we have defined a function loss, and this loss function implements vectorized loss calculation with actual label vector, activation vector, weight vector, L1 regularization rate and L2 regularization rates as arguments. So we set the regularization rates to 0 in case we do not want any regularization. If we set these regularization rates L1 and L2 in such a way that their sum is 1, then we basically get what is called as elastic net regularization. So in other words, for elastic net regularization, we have L1 regularization rate plus L2 regularization rate, their sum is 1. And loss function returns a scalar quantity that denotes the loss on all training example for a particular choice of the weight vector. We'll be implementing only L2 regularization in logistic regression class later in this collab. Next, we'll implement optimization. For that, we'll make use of iterative optimization techniques like gradient descent and its variants like mini-batch gradient descent or stochastic gradient descent. We'll demonstrate gradient descent in this collab, and for that we'll adopt the gradient descent implementation from previous collabs like linear regression. We need to modify gradient update rule that is suitable for logistic regression loss. So there are two steps. First is calculate the gradient of loss function, and second is scale the gradient with the learning rate and use it for updating the weight vector. The second step can be used as it is from our previous gradient descent implementations. However, we need to calculate gradient of loss function that is suitable for logistic regression loss. So we know that the gradient of loss function can be calculated in vectorized form as follows. So we calculate the partial derivative of the loss function with respect to the weight vector W as the product between the transposed feature matrix into the difference between the sigmoid activation vector and the actual label vector plus the regularization rate times the weight vector. So here sigmoid of xw is a sigmoid activation vector of samples. Y is the label vector, W is the weight vector, and lambda is the regularization rate. We implement calculate underscore gradient function that takes feature matrix, label vector, weight vector, and regularization rates as arguments and calculates gradient of loss function with respect to weight vector in vectorized form. In vectorized form, we transpose the feature matrix with np.transpose function, and then we perform matrix multiplication between this vectorized form and the difference between the sigmoid activation vector and the label vector. We add the derivative of the regularization penalty, which is regularization rate, into W. As part of the logistic regression class implementation, we store loss and weight vector in each gradient descent steps as a class member variable. The stepwise loss is used for plotting a learning curve in order to ensure that the model is training as expected. The stepwise weight vector is useful in studying the trajectory of gradient descent in the loss landscape, and we can do this only when we have limited number of features. So in a high dimensional case, or when we have too many features, such a trajectory is very hard to visualize, but we can always print out the weight vectors and see how the weights are changing from one step to the other. So now that we have implemented different components of logistic regression one by one, we will combine them into a single Python class. So we implement a logistic regression Python class with the following member variable. We have weight vector, then loss and weight vectors in each gradient descent steps as our member variable. So we have implemented functions like linear combination. Here only change from our component by component implementation is that we do not need to pass the weight vector explicitly, since it is made a member variable of this class. So we make appropriate changes with weight vector becoming the class member. So here now, instead of explicitly passing the weight vector, we simply have we can call self.w to access the weight vector at any time. Then we have implemented sigmoid function. Then we have implemented the activation function. So the activation function essentially calculates the sigmoid activation for logistic regression. So when we call the activation function, what basically happens is we call the sigmoid function on the linear combination. Then we have a predict function, then we have a loss function, the gradient calculation function, weight update function, and finally the gradient descent procedure. In gradient descent procedure, we we initialize all weight vectors to 0. We initialize the weight vector to 0 to begin with, and then we have two class member variable w underscore all and error underscore all. So w underscore all stores the weight vector after each step of in each step of the gradient descent, and error underscore all stores the loss after each step of the gradient descent. So you can see that here we first calculate, so we run this loop for specified number of epochs. We first calculate the gradient, and then we append the weight vector that was used to calculate this gradient. We also append the loss that we obtained because of this weight vector, and finally we update the weight vector. So weight vector is updated with the gradient and the learning rate. So here you can see that the weight vector is updated to the current value of the weight vector minus the learning rate times the value of the gradient. So this is how the weight vector is updated. In this video, we implemented binary logistic regression classifier from scratch. First, we implemented all its components in vectorized form, and then we combined all those implementation in a Python class. In the next video, we'll use this implementation to solve a couple of classification problems.